everyone, welcome back to another video. In today's video, I'm going to be talking about packing efficiency in solids. So let's start. But before that, I want to address an issue, okay? The issue is that whenever I go on a vacation, okay, and I pack my things, it looks something like this. And I think this is the case with everybody. But when I'm coming back from that vacation and I have to pack the same things in the same bag, okay, it looks something like this. And please don't tell me I'm the only one in this. Please don't tell me because I know it's not the case. So has the space altered? No, the space is the same. The amount of clothes is the same. Okay, the amount available in my suitcase is the same. So what is the difference? The difference is in the packing, and that is what we are going to study today, the packing efficiency. So of course it's quite clear that the first one is a more efficient packing, okay, and efficient packing basically means a better packing because we are able to pack more amount of things in the same space. Is basically what is the efficient packing, okay? So now we'll just extrapolate this concept to our solid state and the unit cells which we have studied priorly. And if you have not done that, you should definitely do that, because for this video what we should definitely know is what is the unit cell, how many types of unit cell exist, and what is the number of atom in each unit cell, okay? So coming to the type of unit cells, we have three different types of unit cells, which is simple cubic, face-centered cubic, and body-centered cubic unit cell. All these three are cubic, which means the basic structure is of a cube, okay? In simple cubic, we have the lattice points or lattice sites only at the corners of the unit cell, okay? Which means a cube has 8 corners, so we have 8 different unit cells, 8 different atoms in this unit cell, but each unit cell is also being shared by 8 different atoms around, so the total number of atoms here in the unit cell of simple cubic is 1, okay? So which means one unit cell is having a total of only 1 atom, right? In case of face-centered, we have, in addition to the ones present at the corners, just like in simple cubic, okay, we have atoms present at each face of your cube. And of course, you know that a cube has 6 faces, which means it should have 6 extra atoms there, but each face is also shared between 2 other cubes. So we have a total of 3 plus 1, which means 4 atoms in this unit cell, okay? In body centered, we have, in addition to the ones present at the corners, we have 1 extra which is present inside your unit cell, okay? And this is not shared with any other unit cell. So this is just belonging to the unit cell it is present in. So it is 1 plus 1, which means it is 2, okay? So number of atoms per unit cell is 2 in case of body centered, 4 in case of face centered, and 1 in case of simple cubic unit cell. And now we can talk about the packing, okay? So packing efficiency, what is packing efficiency? As I already told you about my example of packing our bags at the vacation, which is, I think, a never-ending problem, right? So packing efficiency is nothing but the percentage of total space occupied by the particles in a unit cell, okay? So if I'm occupying all the space available, my packing efficiency is going to be 100%. But we know that 100% never exists. No matter how much we try to do, some space is always going to be left, okay? So packing efficiency can never be 100, understand that. But what is the packing efficiency for all these 3 different unit cells? We'll see that in a while. Okay, so what is packing efficiency? Packing efficiency in mathematical terms is the volume occupied, okay, by the atoms of the unit cell. And these atoms can be 1, 2 or 4 depending upon whatever type of unit cells it is, okay, divided by the total volume available. So total volume available is of a cube, because all these 3 are basically cubes, right? Simple cubic, face-centered cubic, body-centered cubic. So total volume of the cube multiplied by a factor of 100, because why 100? Because of course packing efficiency is a percentage, so we have to multiply by 100, and whatever answer we get is going to be in percentage, right? So now we'll start with the first one, which is the simple cubic unit cell. Alright, so let's try to see what happens in a simple cubic cell and find out the packing efficiency of it. As we already know that lattice sites are only at the corners, okay? And if I just write the formula, we have packing efficiency as the volume of one atom, because in this case we only have one atom, right? Divided by the volume of cube, okay, into 100. Now, if this is the cube, we can consider the side length or edge length of this cube to be equal to A, because we don't exactly know the value of it. So we'll just assume it that it is A, which is a variable, okay? So what is the volume of a cube? Volume of any cube is always side cube, okay? So it's A into A into A, which is A cube. This is the volume of the cube, right? So we have the denominator with us. Now we have to work on finding the numerator. Now what is the numerator? Numerator is volume of one atom, okay? So atom is considered to be a sphere. Although atom is not exactly a hard sphere, but because for the easiness of our calculation, we'll consider the atom to be spherical, okay? And what is the volume of sphere? It is 4 by 3 pi r cube. So we have the numerator with us, we have the denominator with us, we will just multiply by 100 and we should be getting the value, but there is one issue. What is the issue? The issue is that we have two variables here. We have r as a variable, we have a as a variable, and we cannot solve any further unless we establish a relation between a and r. So let's do that, okay? So if I look very carefully in the structure of your simple cubic cell, I can very clearly notice that this is my radius, okay, of one atom, which is r, okay? And this is my one radius, this is my two radius, this is one again my radius, and this is again my radius, okay? So total 4 radius, if I just combine, it is one edge length, which is a, okay? So which means 4 times radius of the atom is equal to a, that is the edge length. Eureka! We have a relation between the two variables which we had, which is r and a, and we can substitute that in our equation and we can find out the value, okay? So if I just try to solve it further, we have 4 by 3 pi r cube divided by a cube, and instead of writing a cube, I can just write 4r cube, alright, into 100. And if I solve this, I will be getting the value 52.4%, and this is my packing efficiency in case of simple cubic unit cell. So only 52.4% is filled, rest all the space is empty. So for a simple cubic unit cell, packing efficiency not so high. Okay, so now let's see what happens in case of your face-centered cubic cell. Let's begin. Well, the same thing is there. We have the formula of packing efficiency as nothing but volume of atoms, okay, which are present in the unit cell divided by the volume of total volume available, which is volume of the cube, okay, multiplied by 100, and it's quite easy. Again, we'll do the same thing. We'll just assume that the edge length is equal to a. So the denominator is a cube, which is sorted. Now we'll only talk about the numerator, which is the volume of the atoms. Well, we have again not here, in this case we have not one, but we have actually 4 atoms in the unit cell. So whatever is the volume of one atom, we'll just multiply that by 4 and we'll have the numerator, right? So now again the same thing, we have to establish a relationship between a and r so that we can find out the answer to what our packing efficiency is. So now if I look at this, these 3 different atoms which are connected, okay, the atoms which are on the face, okay. Now if I just connect these 3, I can see that they are made up of 4 times my radius, because the first one is the entire atom, so it is 2 times radius. Second one is 1 radius, and third one is also 1 radius. So we have r plus r plus r plus r. We have 4r. Okay, so this is the if we just cut a diagonal from the side of the sphere. So now we discuss about what happens in the face-centered cubic cell. The exact same thing happens. The packing efficiency is nothing but volume of atoms, okay, which are present in the unit cell divided by total volume which is available, which is the volume of the cube, multiplied by 100, and that's that. Now in the numerator, now we have not 1, not 2, but actually 4 atoms, okay, because in face-centered we have 4 atoms per unit cell. So whatever is the volume of one atom, we'll just multiply that by 4 and we will have our numerator. The denominator is simply, we'll just again assume that our edge length is a, and we have a cube as the denominator, which is the volume of the cube which is present, okay. Now if I talk about the numerator, which is volume of the atoms, again we have to do the same thing, which is we have to find a relationship between r and a so that we can solve our two variables and we can get the answer. So let's try and do that. Now if we look at these 3 spheres, sphere 1, sphere 2 and sphere 3, these are directly connected, okay, they are connected and they are not having any space in between. So if I just look very carefully, this is my radius r, okay, again this is r, and again this is r because diameter is 2 times radius, and again this is r. Okay, so this entire length, okay, is nothing but 4 times r, or 4 times the radius. And we already know that edge length, this edge length is a, and this edge length is also equal to a. If I look very closely, you can see a triangle which is formed. And what happens when we have a triangle? We apply something called the Pythagoras theorem. Okay. Now what does Pythagoras theorem says? This says that whenever we have a right angle triangle, okay, then the hypotenuse square, hypotenuse is the longest side, okay, the hypotenuse square is equal to the addition of the two different sides, the squares of the two different sides. So we have a square plus a square is equal to hypotenuse square, right? So we'll just put it here. We have a square plus a square is equal to the hypotenuse square, which we know is 4r, okay, which you already have discovered. So it's 2a square is equal to the hypotenuse square. We'll just do the root on both sides. We get under root 2a is equal to the hypotenuse, which is equal to the 4r, which we already know. Now this under root 2a is equal to 4r is the relationship which we were actually looking for, and now we have the relationship between r and a, and we can apply this into our formula. And when we do that, okay, which is the formula is 4 by 3 pi r cube into 4 divided into 4 because we have 4 atoms per unit cell, divided by the edge length a cube. Now a can be written as 4r by under root 2, okay, cube into 100. And when we solve this, we get the answer as 74%, which is very high. So if we compare the packing efficiency of face-centered cubic to a simple cubic unit cell, we already know that face-centered is having a very high value. Okay, it's 74. The other one was 52%, if you remember, right? So now we'll talk about the last one, which is the body-centered. So now let's finally talk about what is the body-centered cubic cell and the packing efficiency of that, and we'll be good to go. Now we know what we have to do. We just know that this numerator, which we have total volume occupied by the atoms, which in this case is 2 because we have 2 atoms per unit cell in case of body-centered lattice, okay, and denominator we have the total volume of the cube, which is a cube, which we already know, and multiplied by 100 we'll get the answer. So let's just cut to the chase. We have to find a relationship between a and r, and that's what we have to do. Now if we find out the relation between a and r, in this case we have to find the spheres which touch each other so that we can establish a 4r relation, okay. So the 4r relation which we used in our simple cubic is this, okay. This side we established as 4r because the spheres were touching each other, which is not the case here, okay. In your face-centered we established a relationship here because these 3 spheres were touching each other, which is again not the case here because the orange one is in between the unit cell. Now in the body-centered, the 3 spheres which actually touch each other are these 3. The one at the lattice side, this one in between, and the one again at this lattice side, okay. I'll just draw it again. So these 3 spheres are the ones which are actually touching each other. This one, okay, the middle one and the corner one, okay. So even though in the picture it seems it's not touching, but they're actually touching each other. So this is the 4r which should be there, right? So again we'll be using the Pythagoras theorem which we used before, but now we have 2 different sides which we have to take into account. If we look at these 3 sides, let's see, okay, this is our body diagonal, okay, this is our A, and this is the another side. So you see the difference in triangle. The triangle which we took in face-centered and triangle which we're taking here are 2 different triangles, right? So this is 4r. This we already know is A, okay, which is the edge length. What is this? This side is nothing but the hypotenuse of this and this side, right? So we know this is nothing but a square plus a square, right? This is 2a square. Clear? So if we just put the Pythagoras theorem, we can very clearly see that a square plus 2a square is equal to our hypotenuse square, which in this case is 4r. So we have 3a square, okay, is equal to the hypotenuse square. So if we just do the root on both sides, we have root 3a is equal to 4r, and eureka, we have a relation now. And as and when we put this into our formula, we have 4 by 3 pi r cube into, in this case 2 because we have 2 atoms per unit cell, divided by a cube, and instead of a we'll be writing 4r by under root 3 whole cube multiplied by 100, and if we solve it we get the answer as 68%. Okay, I'll just write it here. We get the answer as 68%, and 68% is the total packing efficiency of a body-centered cubic cell. And if we just compare all these three, okay, so in simple cubic we have 52.4%. Okay, in body-centered cubic we have 68%, and in face-centered we have 74%, which means face-centered is the best packing, is the most efficient packing, and that is what was the point of this video, to understand the packing efficiency of all these three, to establish a relationship between A and R, which will be of course used for the formulas later on. So if you have any doubts in this video, you can comment that down below. If you want to watch or more videos like this, you can follow this page for more. Thank you so much for watching. Stay tuned for more.